we continue our discussion on symmetry and piezoelectricity, and we'll try to answer this question on which materials are piezoelectric in a little bit more formal way than we did in our qualitative discussion while discussing electrostriction. So let's consider one centrosymmetric material and one non-centrosymmetric material. In a centrosymmetric material, there is a center of symmetry with respect to which crystal is identical. When we apply a pressure, which is also centrosymmetric, it is not possible to produce a dipole moment. Pressure on both sides is the same. And remember that piezoelectric coefficient is equal to change of polarization with pressure. Now, polarization is in centrosymmetric materials, polarization is 0 to start with, and application of for example, tension or compression cannot induce a dipole. Which is a vector. So positive and negative charges will coincide before and after application of the stress. So piezoelectric coefficient has to be equal to 0. There are 11 centrosymmetric point groups, and those materials cannot show piezoelectric effect. And there is one point group 432, which is non-centrosymmetric, but there is so many symmetry elements here that that piezoelectricity cancels. Also, materials that belong to centrosymmetric Curie groups. Curie groups are those which involve infinity axis, as I will show a little bit later, also don't exhibit piezoelectric effect. Now, the remaining 20 point groups and Curie groups which don't have a center of symmetry can all be piezoelectric. And that's illustrated here. We have a non-centrosymmetric material, so material is not symmetrical with respect to this point. There is no element which would map itself on this side. Even though centers of positive and negative charges coincide before, if this atom is exactly in the center of this triangle, application of the pressure can induce piezoelectric effect, can induce dipole moment. So this is just an illustration. So why centrosymmetric materials cannot be piezoelectric? Well, we use for this direct piezoelectric effect because it's convenient. So we start with the material which is completely symmetric. We put it under pressure, and let's say that it develops dipole moment. Now, when we turn it by 180 degrees, this side would have to be negative and this side would have to be positive with respect to the to this situation here. And that's not possible because stress has not changed and material is centrosymmetric. In a centrosymmetric material, however we turn it, we get the same behavior, and therefore we cannot have once for the same situation positive and the other time negative charge. So piezoelectric effect has to be 0. And this is not the case for a non-centrosymmetric material, which is in fact non-symmetrical, and this situation is possible. Now, it is possible in a material to have directions along which piezoelectric effect is non-zero, and other directions in the same crystal along which piezoelectric coefficients are non-zero. We already mentioned that when we were looking at the matrices for different groups. We will now show mathematical apparatus which can allow us to prove this rigorously, but you can play a little bit with a hexagon. Imagine a perfect hexagon in which you have for example, positive and negative charges, the centers of positive and negative, the gravitation center of positive and negative charges coincide. There is no polarization, but when we apply tension or compression, the centers of positive and negative charges will separate. We will have polarization and therefore piezoelectric effect. You should try to find on this body directions along which piezoelectric effect is non-zero and other directions along which it is zero. Now, let's see some examples of centrosymmetric materials. Let us, for example, take 4 over MMM structure. So what these numbers and letters mean? Well, the 4 means that we have a 4-fold axis here. 4-fold axis means that rotating by 90 degrees, I get exactly the same body as I had before. M means that I have a mirror symmetry here. That means that I cannot have a polarization in the crystal because polarization is not symmetrical with respect to the to a mirror plane, and I also have mirror plane here and mirror plane here. So this is a tetragonal material. The structure repeats itself if I apply these different symmetry elements, and this body cannot be piezoelectric. It is centrosymmetric. Another one is ceramic. Now, ceramics contain millions and millions of grains which are oriented in all directions, and even if all these grains are polar or non-centrosymmetric, when we put billions of them together and mix them in all possible directions, ceramic will look like a sphere. Unless we polarize it, which we will discuss next. So, what is the symmetry of ceramic? Well, it has an infinite rotational axis. So this is one of the Curie groups. Here I have to, in this parallelepiped, I have to rotate it by 90 degrees in order to get to the same distribution of atoms. And here I can rotate it by any infinitely small angle, and I always get the same thing. So it has this infinite axis in a 2 direction, and then in the 3rd direction, it has a mirror symmetry. So there is no polarization there. It cannot be created by applied pressure. Now, if we move this central atom, let's say that these are positive and that this one in the middle is negative. If we move it from the center, the centers of positive and negative charges will no longer coincide. We will have polarization. And as soon as we have polarization, we have broken centric symmetry, and material is piezoelectric because it has polarization. And by applying a pressure, we simply change that polarization. If we have this ceramic here and we apply electric field on it, we may orient polarization, we may polarize grains, orient them in different directions, and the symmetry of such ceramic will change and will become symmetry of a cone. So just imagine that I'm applying here electric field, and this sphere and this electric field together, or polarization together, have a symmetry of a cone. So you still have this infinite symmetry. You still have mirror plane, infinite symmetry here, but we don't have a mirror plane here or infinite symmetry in that direction. Many of our ferroelectric materials will look like this, and poled ceramics, and I will explain this term, poled, will look like that. So this is something that is very important for applications and for your work if you work with most of the thin films. So this is what we would also get with induced piezoelectricity. If we take this centrosymmetric material and add electric field, which has symmetry infinity m, together they would have symmetry for mm, and that material would be piezoelectric. So centrosymmetric materials time vector gives you a polar material. Let me just check something. Okay, let us continue. There is a special class of materials which are called ferroelectric materials, and those materials possess spontaneous polarization, which can be switched by an external electric field. That spontaneous polarization must have at least two equilibrium states. Ferroelectrics are a special class of pyroelectric materials. Pyroelectric materials have spontaneous polarization, but it is not reversible with achievable electric fields. These ferroelectric materials usually have a very large piezoelectric coefficients, and that is why they are interesting for us, and we will spend a lot of time studying these ferroelectric materials. So here is an example of ferroelectric, and here is pyroelectric material. Pyroelectric material has polarization, it has a fixed direction, and it has only that one direction of polarization. In a ferroelectric material, I can have at least two different directions of polarization. They are both equilibrium states and can exist simultaneously in the material, defining what we call ferroelectric domains. We will talk more about ferroelectrics later on, but just to give you a little bit of a preview what's happening. Usually in ferroelectric materials you have a zero polarization above certain temperature, which is called Curie temperature. So here is temperature, here is polarization. So we have a zero polarization, material is centrosymmetric, and then polarization sets in at phase transition. So this is usually, but doesn't have to be, cubic phase, and in this specific case of barium titanate, you would have here tetragonal for M, and then orthorhombic, and then rhomboedral phases. And this is the electric permittivity as a function of temperature measured along two different directions in the crystal, showing that permittivity is anisotropic. The direction of polarization for this material changes as we go from one phase to another. And this has great consequences on behavior of piezoelectric coefficients, as you will see. Now, let's say that we take one of these ferroelectric materials. So we have a lot of grains. All these grains are polar. And if we use a single crystal, it can have a homogeneous polarization through the whole material. But crystals are expensive. They are mechanically usually very fragile, can be difficult to make, and we would prefer to use ceramics. What are ceramics? It's assemblage of millions and millions of small single crystals of the size of approximately 1 micron. It can be less, it can be more than that. And we put them together, fire them at a high temperature until they all fuse together, giving us a hard ceramic body. I think most of you know what ceramics are. So let's consider one such ferroelectric ceramic. Now, as I said before, when I make such ceramic, the grains are oriented in all possible directions, and in grains you can also have domains which also adopt separate region with a different polarization. So not only the grains are oriented in different directions, but domains with the grain are oriented in different directions. So the polarization of such material is 0, and that ceramic has this spherical symmetry. There is no piezoelectric effect. However, if I apply electric field on such ceramic, keep it there for a while and then remove it, under the field, most of these domains will orient as far as symmetry allows them under certain crystallographically allowed directions. So we will get net polarization. It will not be as big as in a single crystal, but it will be non-zero. And such poled ceramic can show piezoelectric effect. We will discuss this phenomenon of polling a little bit later, but just to give you this information here, because we discussed ceramics and that's important for our future considerations. Now, it's possible to make polycrystalline material, basically a ceramic material, in which all grains are already oriented in the same direction. And if not, then majority of the grains are oriented in the same direction. So here is an example of zinc oxide. Zinc oxide is polar material. It's not ferroelectric. You cannot reorient polarization by applying electric field, but you can grow thin films in such a way that most of the grains have this columnar shape, and majority of them, let's say more than 90% of them, will be oriented with polarization up or down. That depends on the state of the substrate. So why do we form columnar grains? We form columnar grains because there will be nucleation at of a crystal growth at certain sites, and therefore they will grow more in that direction than they will grow sidewise. So such ceramic will in fact be piezoelectric even without polling, but we have a textured ceramic or textured film. So very often you will find in books that if you have a ceramic, it has to be ferroelectric to be piezoelectric. Ferroelectric because when you apply field, you reorient polarization and you get some remnant polarization, and that give you piezoelectricity. It is in fact possible to have a polycrystalline ceramic material which is not ferroelectric and which is piezoelectric if you orient all grains or majority of the grains in the same direction, and that can be done. So here is a list of symmetry piezoelectricity relations, which you should really understand. This is a list of statements, and you should be quite clear what this means. So when I say polycrystalline material with a random grain orientation can be piezoelectric after polling only if they are ferroelectric. Why? Because they are randomly oriented, and if you apply electric field, only in ferroelectric materials polarization can be oriented. If you have a pyroelectric material which have polarization, but if they are randomly oriented, you cannot reorient them with electric field. And if material is just piezoelectric, like for example quartz, where there is no dipole moment before you apply pressure or electric field, those materials when you make ceramics cannot be piezoelectric. However, if you make a ceramic with all little grains oriented in the same crystallographic direction, then you might. However, this is difficult. You also get statement, for example, all pyroelectric materials are piezoelectric. Why? Because pyroelectric materials have polarization. If they have polarization, they are non-centrosymmetric and they are therefore piezoelectric. Some pyroelectrics are ferroelectric. Well, all pyroelectrics have polarization, but only in some of them that polarization can be reoriented with the field, and that's ferroelectric, and so on. So I urge you to go through these statements and make sure that you understand them. And if you don't, please contact me. There is a small diagram here also, which sort of summarizes this. They are all materials. Piezoelectrics are subset. Pyroelectrics are subset of piezoelectrics. Ferroelectrics are subset of pyroelectrics. Now, I will stop here before we go with trying to calculate piezoelectric coefficients along different axes.